Welcome back for the second part of these diffusion models. So I want to continue today with this topic, and in a way, last week actually mostly covered the basics and the derivation, kind of also history, if you want, in the last years of how these techniques were developed, starting from normalizing flows as the main kind of tool or viewpoint on learning distributions. Hope you remember, right? Working with distributions, preserving the density of the distribution is one of the key kind of components to make this work, dealing with the invertibility to actually ensure that an input distribution stays a distribution throughout to the other side. Score matching as a more tractable objective for learning, dealing with essentially the more local gradients of the distribution, or the log likelihoods. The Langevin dynamics to have this multi-scale approach to allow for sampling. Right? The problem is reaching all parts of a distribution space, even the really unlikely few samples. Right? We want to recover everything. Of course, the mean, all the clustered samples, but also the far away, normally rarely encountered parts. And now, kind of putting all those together, we're now finally coming to the really working and state-of-the-art methods in the form of this denoising models and flow matching as an alternative. In a way, I think also formulations start pretty complicated. In a way, they're getting easier. That's one of the jobs of research, in a way to kind of condense and make things usable and simplify. And then also we can finally get back to some physics constraints. Yeah, let's get started. Diffusion models. Benjamin already mentioned a bit last week. Starting with these more abstract, intermediate, multi-scale steps that we have with these Langevin dynamics. So just having diffusion or kind of Gaussians on different spatial scales as something that works, but is not so meaningful. It's in a way a bit arbitrary. We can now turn to these denoising models that are actually part of what you would call latent variable models that really have, in a way, that provide us with some understanding and a more principled way of treating these in-betweens that evolve in the process. And the idea, probably many of you by now heard about this, is actually quite simple. We are starting, first of all, we are actually now working with different states that we'll call X in the following. And then we'll look at different latent variations of these states in between. Take the same dimensionality, so coming from the vision area, you can think of this as an image. Of course, later on could be a state of a physical model just as well. But we have the same dimensionality here. There's no compression or expansion going on in any way. And now we actually look at a process, again, that deforms such an input at time 0. So here we have t equal to 0 towards some time 1. And this is actually now a noising process. So this essentially destroys our signal. Here we have something that looks like a face, and here we have just pure noise. So this is a bit more written down here. So what we're later on interested in, of course, along the lines of what we treated last week, is something that from nothing, or a simple distribution that we start with, this noise, recovers our original signal. So what we're primarily interested in is the denoising process, getting rid of the noise. That we'll denote with these steps along P, indicated here at the top, or written out here at the bottom as a kind of cumulative application of these different step-by-step distributions along the way, from 1 to t, over all these distributions, starting at a time t, going to a previous time t plus 1, in order to recover the signal at time 0. So this is the direction we're interested in, and in order to make this usable in practice, what we're starting with is something simple, a normal distribution here for especially the time t. But the nice thing is now aiming for something that is usable, here we'll actually deal with really controlled Gaussian noise all along the way. So we'll actually ensure that also the cumulative application of Gaussian noise stays Gaussian, that we have control over the whole chain from start to finish. So this is the reverse direction, and this is actually also the forward process that in a way is a bit more intuitive and that gives us this reverse process. This is now a bit in line with this Langevin view. So we are step by step looking at these different distributions. For the forward process they call Q, and now go from this notation t minus 1 to t, right? So going from the forward process goes in this direction. These now all are Gaussian distributions as well, of the form written out here at the bottom. And now I'll come to the actual expressions for these different terms here in a moment. So especially we have these beta values here that control the spread of these Gaussian distributions. And these we'll actually directly prescribe. So we exactly know how this beta evolves over the course of both the backwards chain and the forward chain. This is an important ingredient here. And putting it together, right, this is actually usable because, right, repeated application or kind of addition of Gaussian noise stays Gaussian, just changes the standard deviation, and the mean gets averaged, but primarily it changes how the spread of the distribution, how large it is in practice, typically growing, and that we can keep under control. And this kind of manual setup of a controlled forward process with a known reverse process, that now gives us a tool to deal with this also coarse to fine view that we had in the Langevin case in a actually even better and more principled way. Previously it was somewhat arbitrary how to scale these different sizes of the noise kernels, and now along this chain we actually know pretty exactly what the noise should be in each step, and we can train a network to do exactly that, deal with exactly the noise that should happen at a certain time. So a few components come in here, of course, for a network. Later on, the time, so where we are in this forward-backward chain is a crucial ingredient, right? So our model later on will need to work with that t here. That's crucial to know. If you wouldn't know where you are, basically it's very difficult to detect the signal underneath the noise. It's difficult enough this way, but this is a pretty crucial ingredient to a model later on. And then once we have that set up, it's actually how we step through this timeline is relatively flexible. All right, let's look at how to actually make that work. So these noise, the noising schedules, as you typically call them, are hyperparameters. So we actually choose how this beta evolves over this virtual time. So important to point out here, we're dealing with a time, right? We have a t here and a lowercase t that's not a physical time. It's a purely abstract noise time. It has nothing to do with whatever we were learning. We could actually learn some time-dependent physical thing with this, but this would be a different time, right? So this time is completely unphysical and only happens for the noise. Important to keep in mind. Yeah, having this noise under control, come to some examples later on. We know what the noise looks like. So the neat thing about this is that at any time, diffusion time, small t, if we have a sample, we can very easily produce just the right kind of data for this time by sampling noise, scaling it with the right amount, and adding it to the sample. So the forward process, going from a data sample towards that times t, right? In the previous slide, we're starting with the image here and went over by a certain amount t. This is now pretty easy. We know this noise is Gaussian, we control it. Yeah, it's actually indicated up here. For example, going from 10 to the minus 4, a tiny value, to in the end 0.02 for these beta values that control the standard deviation. Now, if we write that out, we actually have that under control as a first message. It's a fairly simple expression here that depends on these alpha bar values, and these we have not introduced yet, but these are basically the accumulated 1 minus beta values up to this time t. So they're computed, these alpha bar values are computed in the following way. Right? It's a multiplication of all the alpha s values, where the alpha is 1 minus beta. So it's in a way the residual or the inverse weighting from the beta up until time t. Yes, that's a question. Yeah, thanks for pointing this out. This is one way to write the normal distribution, which is common in this area. It's a normal distribution for xt with mean and standard deviation. Thanks for pointing this out. So it's basically the normal distribution for the x, with the mean being this x0, or a scaled version of the x0, and this being the standard deviation of it. Right, and you can actually analytically derive all these different coefficients, which I don't want to go through here, but the main or the important thing is we basically get a scaling for these mean values and a certain scaling for the alpha values. And the way this is set up, we have a typically some form of transition, a cosine schedule or so. This is a different way. It could also be linear, but actually something with a bit of a flatter tangent at the beginning and end is more common for these. And then for these alpha values, in order to work with it more easily, we actually multiply them all up to the current time t to get the right values for evaluating the Gaussian distribution here. And with this, you can actually very easily, once you have these alpha bar values, it's a bit, right, it's not just a simple single value, but they're pretty easy to pre-compute. They're given from these choices. Once you have this, it's actually quite easy to compute the right samples. So given these samples, we can now also perform training quite easily by looking at the formally you're bound on the log likelihood again. But if you look at this, at first this looks a bit complicated. It's actually quite easy to train in practice. If we reformulate that, you can write it out as 3 terms. Doesn't look much more easy in this way, but now if we look at what is contained in these 3 loss terms, first of all, we notice that the first term here, the LT, does not depend on theta. So that is actually something that in a way does not influence training. This does not influence this reverse distribution that we're aiming for. The last time is also in practice the last term, the L1, for the last step. This is in a way just a residual for the very first step along the forward chain, where we have discrete samples to add a bit of noise to keep it continuous, similar to what we had before actually. Right? In the previous case also we had several times the process of adding noise to get from discrete steps to something continuous. This in a way the same that happens here for the very first step. So what's actually interesting is this KL divergence term here between the forward process and the reverse process. And that I have on the slide here. That is also right in a way pretty easy to evaluate. As mentioned before, both the reverse and the forward process are constructed. We know what these different factors for the Gaussian distributions are. So we can typically input a data set in terms of these x0 values. We know all the different coefficients for all the steps along the way. And then the KL divergence, as before, we basically sample and even out over the course of training, right? We just produce samples and make sure that over the course of training, these two distributions in terms of KL divergence align. This is the typical objective. And right, the different factors that we get out here do look a bit, unintuitive. We have all kinds of combinations of these alpha bar terms, right? So, well, actually, be careful. Some of them are just alpha values. The alpha bar, right? If you remember, that's this 1 minus beta accumulated, comes up quite a few times. Right. This already comes from just reformulating the underlying distributions and working with analytic expressions here for these distributions. So I don't want to go through the details here, but the nice thing is we really know what all these factors are, and then right, it basically means we can directly match the essentially the mean values of forward and reverse process for a certain step t for these noise samples. And yeah, basically this only, and if you look at this is really in a way surprisingly simple objective. We have the current mean value here for our time step t, and this is the mean value that is produced by our network. In this case, for the noise, right? We're looking at the mean of our noise distribution. Right? We have the normal distribution here, and the corresponding mean. And as a training objective, all that's left here is an L2 loss between the true value, which we can analytically compute fairly easily, given all these alpha beta factors. But again, these are pre-computed. And then we just let a network try to predict these, given a current sample. And right, then we're done. Then we're actually learning this denoising process as specified on the previous slide. Now, how does this is still somewhat abstract? How does this actually look like in a real algorithm? If we rewrite that a bit, you get what's commonly called the epsilon prediction, the epsilon denoting the noise here in practice. So if we reformulate this a bit further, we can rewrite our xt in terms of some epsilon value here, now for a normalized initial distribution. And then, right, because this is actually a reformulation of the previous x values, we can train the network to predict the noise here instead of that mean value from the previous slide. What does that look like? If we plug that in here, the mean is actually given by, for these Gaussian distributions, by the following expression. We can have a 1 over alpha term here, and then we're subtracting the noise from the current xt value, because if you look up here, right, this is xt, it basically has right, a certain mean component plus the noise. So if we, from this xt value, subtract the noise part, we're left with the mean. So this is equivalent to the previous objective, and then in practice, we can also, for the loss, focus on predicting these epsilon values. That looks a bit more ugly now. We get a slightly larger prefactor, but turns out that's actually not too important. This is a scaling term, which seems to actually have some negative impact in practice that is left out. Right, so in a way, this just consists of all these alpha beta terms again. In here, the interesting bit is this L2 distance, now not looking at the means, but at the noise itself. And if you look at this, we now have the epsilon, the true noise value. Previously had the mean for the current diffusion time, and that should match the noise predicted by the network, which now receives the actual current sample. Right? This is, if you look at this, this is exactly coming from up here. Right? This is our network receives the current noisy sample as input. It also receives the current diffusion time, and based on these inputs, xt and t, with this it's actually trained to predict the noise itself. This is minimized in terms of L2 objective, and once we have that trained, we can actually also use it in that exact same way to do the denoising in line with the previous Markov process. Right, so important thing, of course, why this works is we're looking at something Markovian, so there's no history, right? Every step along this noising chain is independent. That is an important property I forgot to mention on the previous slide. This makes sense. Yeah, and this now is actually, with that we're moving closer to the actual algorithm. The typical formulation that's used in practice is actually minimizing the expectation of these noise values by dropping the additional term. And I can also now show the actual training kind of schedule after all the reformulations. It's relatively simple. Mind you, we actually do need to fix these beta values, right? A certain range of beta values growing towards the final time capital T. We need to pre-compute the alpha and beta coefficients, but if we have those, then we simply sample the x0 from our data set. We sample a random time t in this diffusion range. We sample random uniform noise, and then from our expressions we can compute the current noised input sample, this xt, with the expression shown here, the alpha bar weight for x0 plus a certain amount of really pure noise, right, that we just produced here. And then we just let the network try and estimate the amount of noise here. And this turns out to be actually a very nice training objective. It's also potentially easier than predicting the mean. The network really just needs to look at this delta on top, the noisy part, in a way that's also been established in a few other contexts as well, that neural networks are pretty good at detecting noise and predicting it. So this is a very suitable task for a neural network. And now we actually have a very tractable, in a way, very simple training objective that's really just looking at these L2 steps for single diffusion times along this chain. In a way, it doesn't get much simpler, right? We are back to very simple supervised learning here. And this does, in fact, enable us to produce very complicated distributions by then applying this model at inference time to produce the samples from the posterior distribution we're interested in. The sampling now directly follows from the initial setup with these Markov chains. So what we now, once this has converged, network is trained, what we can do now to produce a sample from the learned distribution is we can start by pure noise, and now we need to, hope you remember, we basically learned in our image the backward chain going from, went in this direction, right? We had the noise going from the noisy sample towards the actual one. And now we need to go through this whole chain again for the sampling process. So we're starting with a pure noise sample that was on the left side, right? So this is our pure noise with the dimensionality of the data we're interested in. And then we start by sampling additional noise. That's an interesting aspect that we can get to later. Right, for the last step, this is actually 0, but typically we have an additional noise component, the Z here. We do one step with our network, so we take our current estimate, initially the pure noise or somewhat partially denoised sample, let our network produce the current noise amount, then make a reverse step along this Markov chain of Gaussians, that we actually get this factor out of for the noise. This amount of noise is subtracted from X. Then we need another rescaling factor. And at the very end, to make sure we actually follow the distribution of these different Gaussians, we actually need to add some noise on top. So we're actually first removing noise and then adding a certain amount, which is happening with this step here on the right. And yeah, these standard deviation values now again come from this forward chain, and that gives us the next sample along the way, and then we can repeat that. Sample some new noise, perform a denoising step, rescale it, add noise, and so on, and we do this. The standard setting actually for this denoising, DDPM it's called in short, is on the order of 1,000 steps. So you start with pure noise, and then very gradually, step by step, you go from pure noise to the actual sample at time 0. And if that worked correctly, then you have a sample from your distribution. And if you want a different sample, that's difficult to control here, but basically you just start the process with a different noise sample at the top here and do your 1,000 steps again. And then you have a new sample. And in a way, the process is simple. It's 1,000 steps. It's not cheap. But if this worked, you also really get a nice distribution, nice coverage of the whole distribution as specified by your data set. So, and in a way, as mentioned before, the training in a way couldn't be easier. You're really just inputting your data set, and all the rest is given. There are very few hyperparameters. The training objective itself is very simple. So in a way, this is a really stable and attractive setup. The only caveat being at inference time, we do need quite a few steps to produce the samples from our distribution. Right, but in a way now, along the course of our lecture here, coming with all these all these previous approaches with normalizing flows and so on, this is really a very practical method. It's not the fastest one, but really, in a way, pretty powerful and practical method. Yes, there's a question. Okay, yes. So the question was whether, because the exercise is dealing exactly with this process. Yes, good to hear that you're trying it. Exactly. So these samples, these X0, this is a data set, right? This could be 1,000 samples of your simulation or so, simulation states. And then typically you do drawing these random samples, both for time and the noise. These are typically not pre-computed. So the nice thing, I would recommend to pre-compute these on the fly while training. The nice thing about this is that potentially from a limited number of samples in your data set, by sampling the noise, these epsilon values, can produce a huge variability, huge variance in your data, right? So the network has, with this setup, actually a very small chance of overfitting because the noise is really random. It's no repetition. Yeah. If you would pre-compute also the epsilon, there are some cases where actually if you want to do some backtracking through noise, some applications do this, but then there's a larger chance of overfitting, yes. So I would recommend to compute it again every time. Right. Yeah. Yes. At training time to pre-compute this. So the question was whether it makes sense to reuse these steps. I would actually not recommend it. Typically, that is quite fast. Also, producing these is typically not a big workload compared to, say, evaluating your network or so. And potentially, then you run into the danger of overfitting, or I also don't think this is commonly done. But the problem that we still have here is basically we have these 1,000 steps or so that are needed for sampling. That's expensive, right? So we have now a method that produces samples from this posterior distribution that we're interested in, which is great, but it's potentially 1,000 times more expensive than other approaches that we trained before. So in a way, dealing with the distributions here comes at a high cost. Obvious question is, that's also been in the works for several years in the community, can we speed that up? And that's exactly what I want to come to with this chapter here. There are all kinds of ways to speed that up. More obvious ones to kind of shorten this path along the noising chain or denoising chain. So making larger steps or finding different noising schedules and so on. There are ways to deal with this. But what turned out to be even more powerful is this flow matching perspective that I want to discuss in the following. And it seems at first that we are now reinventing the wheel here and dealing with a new look on the same problem, but it's actually still very close. So if you have a working DDPM setup, this is very, in a way, a minor change to switch to flow matching. Yeah, so previously, also for the denoising, we looked at this transformation of different of the distributions. And so we had a chain of different Gaussians of known strength. And now for flow matching, we're kind of going back to the score matching perspective. So the question is, can we do something similar by looking at a flow along velocities? And right, if you have velocities, to get a solution from this flow field, it's typically an ODE that you have to solve to kind of march along the prescribed velocities that are somehow generated or given. And now the main change is that instead of dealing with the changes as prescribed by score matching, we're looking at trajectories for the denoising. So in a way, you can see it as combining the denoising objective with that ODE viewpoint of score matching. And as before, the main task for the ODE integration is that we're given a velocity from a network. Later on, to get sample out, we integrate that over time. What's important to point out here, what is not the most intuitive, but somehow this is how it's established in literature. So for flow matching, we typically target the problem of starting at time 0 for a sample from some random distribution to transform it into a sample at time t equal to 1 that should match our target distribution. So previously we had the other way around, right? For denoising, we had the capital T, the 1000 or large number going down to 0 for the sample, and now here for flow matching, we're looking from 0 to 1 for producing a sample, but that just as a warning before. The objective stays in a way very simple, right? So we're interested in some flow, more on that in a moment. And we train a network now to produce that flow. Right, so now here for this conditional flow matching loss, I want to skip the unconditional version in the script. If you're interested, you can find this in-between step. You can actually write this out as an unconditional version, but here we're already conditioning on some additional latent variable, which is also why it's called phi here instead of the theta from above. But the main point here is we're basically training a network, again, with a very simple L2 loss to produce a certain flow and certain motion. And the inputs are in a way the same. So similar to before, right? Keep in mind, we had going from noise to our sample. We now compute this velocity based on some current x, right? Potentially a noisy sample for a given time t. And this should match some target direction as prescribed by the data, conditioned on a latent variable. For example, conditioned on some endpoint that we have from our data set. Now, so far, this is fairly abstract, right? So this leaves a lot of open questions. Well, what should these velocities be? Sure, we can train a network with for some velocities, but what is our ground truth velocity, the ground truth u here, and how do we connect it to the denoising? So here, some considerations are important. So we're still looking at this viewpoint to map one probability distribution into another one. And we want to start with a simple one and match this with our complex distribution as given by the data. Now, you can imagine, and it's good to keep in mind, I do have some images coming up in a moment. Right. We want to transfer one into the other one. In a way, we are also dealing with something similar for denoising, right? We had the noise, we had distribution in terms of the noise added to our samples. We wanted to transform this into just the samples as given by our data set or the process we're interested in. And for denoising, we actually did not care much about which path we take. We had these Markov chains. We know how the noise should vary along this diffusion time, but in a way, whether our paths are pretty complicated or not, did actually not play a large role. And now, especially from this velocity perspective and this ODE viewpoint, we can kind of reconsider that and say, well, if we know in the end we want to integrate these steps along the way to reach a target, what is the best thing? And obviously, simple steps where you can take big steps forward are ideal. So from this viewpoint of ODE integration, the perfect thing would be a linear path, right? If we had a straight line from source to target, that would mean we can take one of the source points, make one step to the target, right? If it's linear, we just need to know the direction. In one step, we could actually get our sample. So if we could set this up such that the flow from these initial noisy points in our P0 distribution towards a point from the target distribution P1 is linear, we could potentially in one step go from the source to the target. Right? I think from that perspective, it's pretty obvious. And interestingly, it was shown that this also has a nice theoretical motivation. It corresponds to optimal transport. So you can relate this, right, basically in terms of distance and mass being transported. This is also optimal in the sense of minimizing both the distance and the probability mass to be transported from source to target. So there is a nice theoretical formulation for this. And right, it's actually kind of fun to draw this out. Or to kind of just highlight the differences of these viewpoints. So for just as a reminder, for the normalizing flows, we actually stuck to a very rigid transformation between the distributions. So here on the left side, we have a simple, something like a Gaussian distribution on the left, and some potentially more complicated, slightly more complicated is one example, target distribution here on the right. And just as a reminder, in a way, we had the same target for normalizing flows. We just had this constraint that we're dealing with perfectly invertible transformations in order to work with these Jacobians in a more convenient manner. I hope you remember. So this constraint, in a way, is a deal breaker for normalizing flows. This is too restrictive. This does not work well in practice. That basically made us turn to the denoising models, where again we are starting with pure noise, a very simple distribution. We want to go to the target distribution of the actual samples we're interested in, right? These now would be prescribing the mass of this density here in our 1D example by just density of points. And for denoising, as mentioned before, this actually does work quite nicely, but now in a way we don't care so much about how to map these initial points on the left towards the target points. So what in practice also what you can really measure and what happens is these paths make all kinds of curved lines. Right? They're typically not too wild. Also networks, this would be wasteful, are fairly resource efficient in terms of their parameters and so on, right? So we don't get weird zigzags here, but the curves can intersect. They're definitely not straight. And now, right, the obvious idea for flow matching here is, right now, we want this to be simple and straight. We want to find a mapping that, ideally with a line, maps points from the source distribution to the target. That means also they shouldn't intersect in this picture, right? We don't want these to cross or to be curved, but ideally go in one step from source to target. And yeah, in this formulation now, if this works, I come to the moment, it's tricky to really make that work, but at least by adding these constraints, you can significantly reduce the number of steps. Then we could theoretically map from the source towards the target in a single step, because the direction would change. It would not help to make more steps along the way, because the direction would be constant. And that being said, as a warning, it is actually tricky to make this work with one step, because it's also, I think, a good thought experiment in this context. If you think about what that would mean if we would want to go from one step, from pure noise, to the target in a single step, that would mean going from something that has no information at all, right, pure noise, towards all our targets. But this is a really ill-posed task. So, right, we have no information, and we want to go to all our samples. If we would try this, if you try to train a network to do this in one step with a supervised objective, what does supervised give us? Mean value, right? If you train for one step with supervised, what you will get is basically a network just learns the mean of your data. Maybe something like this in this example, right? The network has no information. It cannot possibly learn much. You're inputting a lot of data as targets. It will learn the mean. So one step as a direct objective actually cannot work. It only works because we're looking at the whole space in between. And there the network can start to figure out parts of the noise and actually start to also give you different solutions. Yeah, so I still haven't mentioned how this should work. Luckily, it's also starting from this relatively complicated formalism, relatively simple to set up this objective, simpler than DDPM actually. We need to first keep in mind a certain minimal noise amount, again to preserve a continuous distribution. We want to get away from the discrete samples, and then we can set up the generating distributions and the velocity in the following way. This looks a bit ugly because we want to stay away from a time value of 1, which would mean no noise at all. So we have, if you can look at it, we have all these 1 minus sigma min terms here. So I've written it out down here without the a sigma min. So if you keep in mind, right, we're not going all the way, we're always keeping a certain small amount of noise. But what this then corresponds to is, for our distribution, we simply have a now written without the target variable, right? It's just a mean. We have a mean of t times the target value, the x1, and 1 minus t times as a standard deviation. And as a velocity, we now have the expression here at the bottom. And this is really just, we can see it, right? This is a direct step from x to x1 divided by the step size. In a way, this is exactly prescribing the linear velocity. You're producing a current noise sample similar to before with a certain distribution, and then we're training a network to go with a single step straight from our current sample to the target sample. Right, and if you keep this in mind and now look at these again, this is still the same, right? So basically you have x1 minus 1 minus sigma times x, and down here you have 1 minus sigma times t to account for that the kind of slightly shortened interval of this range between 0 and 1. Yeah, so in a way this further simplifies the whole process. Nonetheless, it's often a good start to also have DDPM in there as comparison. So from our experience, DDPM still has a slightly better, it's a bit more costly, but also has a slightly better spread in terms of the target distribution. And this flow matching works very nicely with few steps and still fairly good, but sometimes you can have slightly worse performance in terms of the distributional accuracy, if you want. Now, there's one other difference that I want to mention here. I mentioned before, these alpha-beta terms play a crucial role in DDPM. It's actually fun to look at those for the normal process. So for a typical noising schedule, this is actually what the alpha values look like. So here for 100 steps, so these are the alpha bar values in orange, right? So this is the progression in terms of targeted reduction of noise, and these are the beta values, the blue ones. Now, what's interesting is if you look at how they're used in DDPM, if you plot the factor here, the 1 over square root alpha, right here it's really not an alpha bar, but the alpha directly, so 1 minus beta, then unfortunately it's 1 over something. So if your alpha, the alpha t here is very small, meaning the beta was close to 1, which is actually the case here in these later steps, then 1 over something tiny will potentially be pretty large. So these values look pretty well behaved, but this 1 over squared alpha factor is actually not. In the beginning of the denoising, towards the first steps, now this is actually shown here for the same progression, these can be pretty huge. So potentially they're even larger for a larger number of denoising steps. And if you now look at what these terms do here, they actually make these x values zigzag a lot. It's a bit, I hinted at this before. So first we actually subtract the noise quite a bit to recover the signal, but then according to this noising process, we need to scale it up. So you always first subtract to go to a value, and then you scale it up to get to the right value. And if you look at what these factors do in practice, is you actually get these zigzagging motions. And especially in the beginning, actually the first steps really reduce the noise by a lot, and then scale it up again to here to get to something close to the mean. And that means if this prediction of your noise was just slightly off, down here or here in one of these values, you multiply this by something really big and blowing it up. And this can actually cause problems. So DDPM in a way is very nice, and it is a good objective, but if it's slightly off, it can nonetheless go wrong. And then typically, if it's not really well trained, the training might nicely converge, but nonetheless, in certain cases, when using it at inference time, you actually still might see that certain samples blow up, or your network might not produce reasonable samples at all. So this behavior is something problematic, and this does not happen in flow matching. So nice thing about flow matching is there's no zigzagging. Flow matching really just starts at a certain value. Okay, draw a different color, right? And then we basically, this example would linearly go down. You have one time the noise, and you just reduce the noise by all the steps down to no noise being left. So I think this is a more intuitive indicator for why flow matching is actually more stable and more well-behaved than the DDPM here. Yes? The question was whether this corresponds to a training curve. No, this is not related to training. This is really inference. Whether this inference is a training behavior, that's a good question. I have not looked into this. Yeah. Mm-hmm. Mm-hmm. So the training can be somewhat noisy. We tested these hyperparameters internally, basically, and they work quite well. I have to admit, I don't know whether batches that have potentially more early times here from this more strongly zigzagging period, whether those also show up as less stable training time. I have to admit, right, you could potentially see whether the noise at training time correlates to basically at initial noising times close to the capital T range. Would be interesting to look at. Right, out of my head, I wouldn't know. It can be noisy. I mean, overall, the training should be fairly stable because it's an L2 objective. It's not a simple one, but it is a stable objective. So if you have the right hyperparameters, it should not be. Mm-hmm. Would be right. Good question whether these zigzags correlate to potential jumps at training time. Yeah. Right. So I do have this in on the slides as a summary. So as a more intuitive explanation for the even a more improved behavior of flow matching compared to the DDPM, which is already compared to the other normalizing flows and so on, and even score matching. A nice improvement, but this flow matching in a way is really surprisingly simple and stable in this context here. Yeah, so also the final algorithm is really simple. As mentioned before, you basically sample your time, you compute this xt value with a weighting, right, with this 1 minus sigma term, but basically it's just 1 minus t x0 times t x1, and then the velocity is given by the difference of the two. And at inference time, you just integrate up dt times whatever velocity your model produces. So of course, also this being a simple ODE, you can use higher order ODE integrators. From our experience, actually, it's usable, but it doesn't add too much. The path is relatively straight. These higher order integrators don't give you a lot of improvement, and typically also need more evaluation steps along the way. But it's of course usable here. Yeah, also if you want to look at a direct example comparing the two, there's one in the book here. And both denoising, I think it's more slower, but potentially also something to still keep in mind here. But especially flow matching, I think is really also for times to come, for the foreseeable future, a pretty powerful tool. So I do want to show some examples that we encountered in previous work here. One being this airfoil case that I've shown before a couple of times already. And now if you actually look at varied states, we're going to have a flow around an airfoil. I don't want to go into too much detail, but also from our experience, this DDPM was the first method that can really learn a distribution. There were others in the field before. These Bayesian neural networks were, we also covered actually in the lecture a couple of years back, were promising back then, but don't work. They have a hyperparameter. These 3 lines here, depending on what you put in manually, you get different things out. This is unfortunately pretty useless. Other things like these heteroscedastic models, you also have to prescribe a distribution, but you don't actually learn the correlations in your data. It cannot produce good samples. And the DDPM variant kind of hiding here in these pink lines. Oh, I do have some arrows, right? So ground truth is actually the black line. The blue one is this prescribed variant. And the red one here is the diffusion model. This really learns. What's shown here is actually a standard deviation of the sample, so that the samples really based on a hyperparameter should vary more and more in a certain way. This is just learned based on the data, and this is actually something that previous methods in a way could not do. Let me quickly just show some of these samples in motion, right? So at the top you can see different outcomes now for one set of input parameters. You can have very different answers. If you prescribe these, right, like a Gaussian distribution in terms of mean and standard deviation, the model will learn what it looks like, but then every sample here basically has these. So forming these into a coherent solution is actually not possible here. You get very noisy and arbitrary solutions. So from a physics standpoint, right, if you're looking at a flow field, this is completely useless, unfortunately. And also these BNNs didn't work, and these DDPM values now produce these samples. You cannot choose which one, but in this case, actually it matches this one sample here quite well. And this is potentially now also a bit more difficult to evaluate whether the model worked, right? You're dealing with a distribution. If you run your model, you don't know which sample you're going to get. So the best thing you can do is to actually, at least for evaluation, produce a very large data set of reference solutions, and then you can look for the closest sample and check how well it matched. And then you can, or you kind of need to use distributional metrics like Wasserstein distance or so to compare the distribution of your test set and the one produced by your model. Yes? So it has a conditioning here on a certain flow direction, but all these answers here at the top are now valid outputs. So you can imagine this like being different times. Imagine you have something unsteady with different, right? And you have flow from a certain directions, and all of these states are allowed, exactly. It's like ignoring time. The network is just now has a task to produce any of these samples from time, but we don't know which one. All of them are, in a way, valid, but of course also some might occur more often, and the network should produce those more often. Some are very rare, and then it should produce these once in a while. Right? So it also needs to respect the probabilities of how often these different samples occur. But exactly, this is actually, also just quick comparison. So also for this scenario, the previous example was DDPM denoising. If you compare this to flow matching, in this case, it's now the next red line here. So now DDPM is in blue. Both learn the distribution quite well. And for this case, flow matching with around 10 steps was mostly on par with what DDPM produced with 200, so a factor of 20. faster for sampling and producing these. But still, right, n equal to 10, meaning here it needs 10 steps to produce the answer. It's still 10 steps slower than the deterministic single-step network. So if your targets are actually not random, if there's a unique mapping from input to output, then potentially you might not need this, right? Then you can actually be faster. It's also something to still keep in mind here. But if there's ambiguity in your targets, this does pay off. Exactly along the lines of what the question just was, we also looked at this for a bit more complicated case in 3D with an airfoil. Now really a 3D airfoil wing with an unstructured input mesh. And then here are some samples of what fairly turbulent flow over these wings. I forgot the exact Reynolds number, but it's turbulent looks like. Or here's another wing profile. So I have all kinds of different geometries and torsions, only wings, but in different geometries and pretty turbulent configurations. And now also in practice, when we want to simulate these, what we're actually interested in are these developed, right, plausible states for the chosen Reynolds number. If you simulate it, however, you need to start with some initial condition that is usually unphysical. You need to wait a while until the disturbance has developed, until you're actually in a regime where the states become more physical. And only after that time, then your simulator, a classical one, would produce interesting data. So cases like this are actually, in a way, pretty expensive, simply because you have a certain warm-up time that is not physical, this initial transient stage that you throw away. Then afterwards, you can start running your evaluation and see whether your wing is potentially stable or has too large of a pressure in certain regions, or run some statistical analysis afterwards. But such a scenario where we're just interested in these more or less steady states, and we actually don't care about these initial ones, is also a very good one for these probabilistic learning approaches, because then we can just treat this part here as a distribution and give the network a task to basically not be aware of time, because also in this case, usually we're not so interested in the exact consecutive change of the states over time. We just want to know, how likely is it that we have a certain pressure spike, or what's the average force distribution on in terms of lift or drag that this wing experiences. So our network should just produce now these different states from this developed equilibrium stage, but we don't care about the order anymore. This now nicely fits into this distribution viewpoint for the probabilistic models. So, this is actually an example from a paper where we trained a network to do exactly this. And I'm showing this because it did work nicely. So this is actually one of Mario's work. So it uses GraphNet internally, as discussed a few weeks ago. But the architecture of the network actually for the diffusion is not too important. And there are two variants here. There's one that directly does the diffusion process on the graph, called DGN here. And then there's an LDGN, where we first train an autoencoder to compress this into latent space. Then you run diffusion on that latent space, and then you kind of decode it again onto the target geometry. Those are in a way quite similar, but this latent version had some nice side effects of, again, projecting out some of the remaining noise. So it did work slightly better, and it's actually faster because potentially you can compress the size of the space the diffusion needs to work on. So these are the two main versions in the following. The left side now also shows this denoising process on the geometry. There's now one of the sample geometries, and exactly as shown before, we're starting with pure noise, and then step by step the denoising reduces. Also flow matching here would work just as well, reduces the noise to produce a sample. And now for the evaluation, what's also shown here is again a match of the different samples, right? So if you get one of these outputs from a diffusion model by itself. You need to now scan basically through your data set to see whether the sample was actually, or how close the output is to one of the samples in your data set. This is now here in terms of ground truth actually the closest sample we had in this for these test cases in the pre-computed data set. The other version here at the top right, this GM, the Gaussian mixture model, also one of the more classic alternatives to learning, fitting basically multiple Gaussians. This had severe trouble with a relatively large space of these 3D cases, just to show, right, this is really a non-trivial scenario and did not work, and this actually did not produce a valid sample for this case. Yes? Mm-hmm. So the question was, right, if I pre-compute the ground truth samples here, right, I basically have many different samples in a data set, and then it could happen that I run my evaluation. If I would now produce twice as many samples, maybe suddenly I have one that looks closer to this one also, right? Yes. Well, you can check how the distribution of these ground truth samples evolves at pre-computation time, right? You can track basically standard and mean and standard deviation, for example. So this is something we did check here. We cannot guarantee in these cases that not if we would run it 10 times as long, we would suddenly have something that looks exactly like this. But we did ensure that we have very stable mean and standard deviation ranges for the data. So in a way, I'm quite sure that the distribution for these ground truth samples was stable already. So it's at least I can confidently say that it's very unlikely that this state would show up, but it could happen basically. But with these scenarios, I can recommend basically look at large enough samples from your distribution. If, for example, a good check is, right, if you make it twice as large and it doesn't change much, probably it's pretty good. But this is something you need to also take into account for every case anew. And of course, where this could be interesting, if you have something like extreme events, also for wings, we might be interested in actually, right, the largest possible pressure spike that could locally occur. If we're interested in very rare events, we need to make sure that for training data set and also for evaluation that we have enough of these extreme events. So that is potentially something that's actually critical. Here we just looked at mean and the first few moments of the distributions, but not too much at these extreme cases. Then you probably need even larger sample sizes. Yeah, so this is in terms of, right, sample accuracy. Mentioned before, this is in a way only a single view. What's more important is really the accuracy of the whole distribution. We have something very high dimensional here. It's actually not trivial to compare high dimensional distributions. What we used here is, or what's shown here is just in a way a cross correlation between all the samples. This turned out to be a pretty good metric. You can also look at these Wasserstein metrics again as a kind of move density and distance weighted metric, and they're even, I think, for different fields, even more potentially more complicated, more reliable ones. We found this one to be a pretty good indicator of, say, Wasserstein and others, but this is a non-trivial task from discrete samples to reliably estimate a high-dimensional distribution. Nonetheless, that being said, but the GNN version, for example, here really does pretty badly with a coefficient of determination of 0.6. This DGN variant is almost at 0.9, and this latent space variant is above 0.95. So in this case, the this kind of regularization with the latent space additionally improved things. What you're seeing here now is also the standard distribution over the wing. If you now look at what's shown in these different images, right? So here it's obviously very red. If you compare this to the ground truth, this is quite bad. If you compare the DGN version, for example, with the spike here at the front of the wing, this is recovered quite well. The DGN version here seems to have a bit of a noisy standard deviation, but it recovers a bit more of these peaks on the top of the wing, but this is potentially still actually also, even in this case, right, these values are not fully on par with those of the ground truth. This is where this remainder potentially comes from, especially the kind of spikes, the outliers in the distribution are actually what's difficult for these methods. Yeah, also here the paper, we did measure performance. I don't want to go through all the numbers, but if you compare basically the whole trained network against what was necessary to produce the samples, there was a huge speed up here. Part of that comes from not needing this warm-up phase and then the network being relatively fast. In a way, this is also a good scenario to use these models because the actual generation process is quite slow. Yeah, so that as an example of using these distributional or probabilistic models in the context of physics applications. But also one point I want to come back to today is we looked at all these priors, or the PDEs, right, our formulations, our knowledge of what should be in the physics. Can we get that back into the picture? Because even the previous wing case was kind of just using the data. It's in a way, as mentioned before, for both denoising and flow matching, it's a fairly simple supervised learning objective to recover these distributions and not using any of the physical knowledge. Now, if we keep that in mind, we want to bring more of our understanding of these different processes into the picture. How can we do this? If you think about it, there are two main options. A bit obvious, but it's not so trivial how to pull it off. We can either try to use the PDE at training time, or we can try to use it inference time. So basically, we try to train our model with these physical priors to get a better model out, or we can use these physical priors at inference time to produce a better sample in this case. And both are valid options. So in this context of the working alternatives here, the both denoising or flow matching models, at inference time, if you think about it, the main step we are doing here, where we could use a physics model, are these denoising or flow matching steps, right? Where we kind of go along the chain to produce the final sample. So one idea, and it's already an interesting one, is, and potentially a good one, to use some physical prior, some physical model to improve how we go along these steps to get a better final output. Another variant is, in a way, using a similar physical model at training time when we're training for these objectives to then give us a better trained model. And I do want to briefly give examples of two methods that fall into these two categories. So this is pretty recent. These are pretty recent developments. So I don't want to say that's the end of the line for both of these options, basically, but just to give an example of how it can work. If we're looking at inference time, so we're basically training a normal generative model, DDPM, for example, potentially also would work for others, then what we can now do, this is just the normal DDPM inference procedure repeated from before, right? So we have our noise samples, we have these the predicted noise subtracted, being added. Intuitively, what you can do is, after this step here, we have a new sample, right? The xt minus 1. If we know there are some constraints here, for example, should be divergence free or something like this, we can now check, is this actually the case or not? And potentially, we could now do a step along the direction of this constraint towards something more divergence free, or something something in the direction of upholding some other conservation laws or constraints that we might have on the system. And that's in a way what these physics-informed diffusion models that were proposed earlier this year actually do. So what what's necessary ingredient, what I didn't mention before, is it does not work out of the box. You need to actually approximate the target value, right? So the xt minus 1 we have here is potentially, especially if we're looking at a large t, something that's still very noisy. And anyone who's tried to use physics on noisy values knows it's not a good idea. If you compute derivatives on a noisy signal, right, potentially your noise blows up even more. So you need a certain projection step. That's typically known as Tweedy's formula, or also PIDM is a method to do this, where you go from this step t minus 1 down to 0 in one step. So kind of based on the current state, try to predict what's at time 0. Hopefully this is pretty good. That gives you some approximate x0 value. On this, you now evaluate the physics constraint, and then you make a step or a partial step along this direction. Right, so what they do in practice is, with some additional learning rate, lambda, and some physics constraint, go along the gradient of that constraint towards the target. Yeah, and then you basically repeat this. So that, as they argue, basically step by step helps you to enforce these physical constraints along the way of the diffusion chain. It's typically also no full guarantee. What's a bit a danger here is you're basically changing the directions of the steps of the denoising. You're basically pulling them towards the solution of your constraint. And this can actually modify the distribution of the values. So this is actually a paper from our group, why we came up with an alternative that does this at training time. Now the main constraint is in a way very similar. You also vary the same gradient along that constraint basically, but you do it at training time. You need the same step. You have something noisy. You again need to project it onto a reasonable sample. We actually did use flow matching here in this context with a few steps to get a good estimate here, but in a way this is a smaller change. Now, what turned out to be more important is, if you do this at training time, you basically get two different directions. You get one direction for your flow matching loss, try to learn the velocity, and then you get another direction for this physics constraint, in a way similar to the two directions you're following at inference time in the previous approach. So these can actually be in conflict. They might drive your network towards different directions. And what helped here is to use a special optimizer in a way. Also another method from Chang, from our lab actually, that we called config here, that processes these two directions and then gives one learning direction that in a way gives you a compromise direction that conflicts with neither of these two initial directions, or kind of removes the conflict between the two initial directions, makes the steps along one step along that direction. So that, from our experience, actually really helped to use the directions that you get from these physics constraints. This is a bit more costly at training time. You basically need to evaluate this physics residual at training time, and potentially you need to evaluate it separately, so it is twice as slow as normal training. But the nice thing is, once you've trained it, it's same cost as the regular denoising or flow matching, because the physics constraint is out of the picture. Then you just have a network that better reflects the physics constraints, but there's no additional cost. Yeah, if you're interested, the whole algorithm is written up here. So right here we have the velocity produced by the model. Then here are actually multiple steps to produce an estimate. This estimate x1, that's a physics residual here that's being computed. Then you have two losses that are evaluated for the residual and the flow matching loss. And then in this step is this conflict-free residual with which you actually do the training. and then you just keep on iterating on those. And we actually did compare these different methods now. Here's just one example in terms of the distribution. I want to skip the actual images. It's a relatively simple kind of Darcy flow case of a porous medium. But what's interesting here is that this previous method that takes steps along the physics gradient, the physics residual at inference time, gives a very low physics residual. So it seems to do great in terms of physical accuracy, because it really kind of enforces those constraints later on when you evaluate the model. However, if you look at the solutions you get, so on the right side here, you have the distribution over the different pressure values. If you look at the tip, it actually has a lot of mean values in this purple, and then also here on the side, this is the cutoff for the spread of the different pressure values. And yeah, this is a log scale, so it really overshoots by quite a bit at the top. And right, does not recover any of these outer regions of the distribution. So that's what I indicated before. It basically, most likely from the physics residual, kind of overshoots to the mean value. And in comparison, the combination that uses this residual at training time, the full one is actually this green one here, this one. And it also has, there's some part that actually, somewhere around here, that recovers this range of the distribution. So some of the really rare cases are still missed, but at least it has significantly improved distribution, and actually is a bit faster because it doesn't need to evaluate these physics constraints later on when it's being used. Yeah, so in a way, all these distributions do, I think, make these methods very practical, because many cases have uncertainties. We often don't just have a single answer, but it makes both inference more costly. At training time, we have these additional dimensions for recovering a distribution. So it is a bit of a trade-off, but nonetheless, these methods are really powerful. And here's a very aggregated overview and summary of all these topics together. So I think it is really a powerful class of methods. Dealing with these complex distributions really is a very different task to the normal supervised learning, and from deterministic setting, and these techniques, I think, are really also pushing the boundaries of what's possible in the whole computational field. So I think from that perspective, this whole deep learning methodology in this area really already pays off. This is a very interesting future capability to deal with these complex distributions. In terms of learning, right, it's actually in a way surprisingly stable and can deal with pretty large, high-dimensional problems. And right, potentially is actually really useful for a variety of downstream tasks, like these simulation-based inference scenarios that were mentioned in the beginning by Benjamin, and also the uncertainty quantification areas, I think, are important for a variety of real-world applications. Just to name some, I think there are a couple of other interesting opportunities down the road. Right. That being that being said, there are also negative aspects. They are more expensive, both for training and for inference. So if your case is actually not probabilistic, if there are no uncertainties, then there's very little to be gained. So in a way, it boils down to the classic a problem or challenge. Well, you should know what's in your data, or the more you know about your data, the better you can actually set up the task and make use of it. If you're just learning a lot of mean values with this, potentially it can also work, but it might be slower than necessary. Right. Also, there is, especially for the inference cost, the community is working on this quite actively. I think things will improve, but potentially it is definitely not the cheapest method in the area. All right, so much for the probabilistic models. That also concludes this chapter. Next week we have a different perspective on the whole task with the reinforcement learning viewpoint. Are there any questions at this stage?